If our speakers could come on and say hello. At first, I'd like to introduce Jim Johnston from McElroy. Jim, could you introduce yourself and tell us who you are and what you do?
So, hi, I'm Jim Johnston. I'm the Chief Technology Officer here at McElroy. So I get involved with a little bit of everything, but specifically for today's purposes, a lot of the discussions around standards and sit on a lot of the standards boards around the country and around the world, actually.
Yeah.
So.
Yeah, you do. And we really appreciate your work, Jim. And some of the products you produce at McElroy are fantastic. So thank you for that. And thanks for giving your time today. Chris Waite from SECOR. Tell us a little bit about yourself.
I'm Chris Waite. I'm a branch manager in outside sales for SECOR out of Gillette, Wyoming. I do everything from field work to fabrication to selling of the product, and help out as much as I can anywhere I can.
Well, you're also one of those guys that's finished the Certified Professionals program, Chris, and a big supporter of the Alliance. So thank you for being there. Carl, I'll just call him Carl V because I have trouble with his last name. Carl, why don't you come on and tell us who you are? And you've got some of the coolest projects going out there in cold weather.
Sure do. Thanks, Peter. Carl Vruge. Vruge is how you say it. Think Scrooge, but with a V.
Well, that's fitting.
Yeah, it works. It works. Yeah, I'm with GF Eurocon, National Sales Director. Been working with HDPE pipe specifically on freeze prevention type projects in cold weather for 25 years. So I get to go to all sorts of exotic places like the UP of Michigan and Alaska and northern Manitoba in February. It's good fun. Happy to share some stories today.
Well, we're really glad you're here, and thank you for that. Okay, moving along. We also have a bench. I'm not going to ask these folks to come on, but we have a lot of talent. And one of the things I'm trying to do with the Alliance's webinar program, everyone, is treat it. We have two programs going on. We've got the bench and also the main show. And we're hoping that you're going to use Q&A as your function, not chat, to ask this bench questions related to cold weather or not. Any question. We've got a lot of talent here. And we thank these folks for donating their time to helping us produce this. So treat it as office hours, if you will. So today we've got Jim Johnston, Chris Waite, and Carl as primary. And we also have the bench. So ask away your questions and send emails to the team and say, hey, can you help me with a project? And we will do that. I also wanted to mention that McElroy's got a fantastic training program, as does your preferred distributor. So if you need people trained up on HDPE Fusion, talk to your distributor or McElroy and they'll make it happen. McElroy also has an inspector's class that is totally online, and they do not have to be qualified in any type of fusion prior to that. And also Integrity, Rick Ponder was going to join us today, but they also have an electrofusion class available to people to take to become qualified in electrofusion. Okay, with that, we're going to move along. And really appreciate your time and getting through some of this stuff. So inclement weather is a generic term that is just not perfect weather. And how often is that? Well, probably 80% of the time. And it can be rain, can be snow, can be wind, could be urban areas, things you do. So we're talking today about inclement weather, but mostly cold weather. So interestingly, the Plastic Pipe Institute says that their limit for cold weather is 32 degrees and preferably 40. So if you're doing butt fusion operations or electrofusion in temperatures below 32, according to their guidance, you should be controlling that fusion zone either with a tent or with some sort of structure to make it easier for the fusion tech, but also to make the fusions go a little bit more easily. One of the things I love about this image is that the operator has cleaned the snow up to about 4 or 5 feet away from the entrance to his cube. That's so that none of the snow gets in there and melts. Obviously, we're melting things, right, during fusion operations. And then on the electrofusion side, most electrofusions can be installed to 14 degrees without protection. But the rules that apply for butt fusion also apply for electrofusion. So please consider that when you are conducting operations. We generally like to say that 90% of your fusions are going to be butt fusion unless they're not, right? So the other 10% are electrofusion typically, or sidewall fusion. So you need to control for electrofusion every bit as much as you need to control for butt fusion. And what do we consider important? We consider controlling the fusion zone to be extremely important. Thank you to Brady Fuller from Jacobs in Oregon for sharing these images. He won an award for one of his projects from the Alliance last year, and he regularly conducts his projects in colder weather. So here we see some tracer wire going on a valve, and that valve has a mechanical joint adapter going into it. If you didn't want to use an MJ, you could use one of AVK's Series 66 that has pup end on those valves instead of the traditional female end. So thank you to Brady Fuller for that. Excuse me. And then Cash Weber from Core & Main shared these images from Alaska, where he's using, it looks like, 2 containers as his protected fusion zone with a roof cover using a tarp. And I'm sure he has something like a salamander heater in there. And notice the pipe that he's using today doesn't have snow on it yet. The pipe in his storage there in the left of that container still has the snow on it. So we're asking you to remove the snow and other wetness, if you will, that could occur. The other thing that I love about that image on the left is how easily that polyethylene pipe, typical lay down area for polyethylene pipe. So thank you, Cash Weber. And then we have Adrian Harmon from Great Pacific Consulting, a contractor who responded to our request for images. I mean, look at this. This is in the Canadian Arctic. This is 10-inch DR17 polyethylene pipe strung up to a depth of 2,200 meters. And this ended up going into the ocean to a depth of 42 meters. Then they sent divers down to make sure that the diffusers were working properly. So check out this image or this movie.
I'll help with the sound effects, Peter. It's going.
You couldn't hear the sound?
No, sir.
Oh, I'm sorry about that. Well, needless to say, this is not a typical polyethylene installation, but this is a diffuser operation in a mine, and polyethylene is the only pipe that could survive this sort of condition in a diffuser. So kudos to our friends at Great Pacific for sharing. And another thing, Alan, if you could come on and tell us, why concrete anchors on these DR9 24-inch diameters. What's the purpose of the concrete and how does it work on top of polyethylene?
That's a great question, Peter. Thank you very much for asking.
Alan Ambler?
Hey, can you hear me? You hear me fine? There you go.
Yep, we can hear you now.
Perfect. So the reason why these concrete anchors are on here, Peter, is because the HDPE is buoyant, so it actually floats on water. They will design and know the buoyancy of the line that they're installing to such a degree that the concrete anchor will be placed upon there. Then once they fill the pipe with whatever fluids inside of it, it'll settle down and sink to the bottom of where it needs to be. Then they can drain it and look at the pipe for maintenance operations or other things like that. So, Pete, did you want me to send the poll out to everybody?
Yeah, let's do that. Let's send the first one out now and let's wait, a few minutes, about half an hour for the next one. And also, as Alan's doing that, a reminder to our guests that this is a 75-minute webinar and we will finish right after 15 minutes after the hour. Alan, let's take a look at that poll.
They were both grouped together, Pete, so everybody will read both questions together.
Okay, good. While they're doing that, Alan, could you tell our audience how they get their PDHs or CEUs at the end of the talk today?
Absolutely, Pete. Thank you for asking. So we did get that question, and we've gotten multiple questions from the audience there too. So definitely keep those questions going. At the end of the webinar here program itself, the very first question of the survey will be, what is your license number and your email and your name, so we can send you that PDH that you need to be able to satisfy that requirement. So definitely wait till the survey is queued at the end of the webinar. That'll give us the information, and it'll certainly make it a whole lot easier for us to process that for you and send you that within a week to 10 days.
So Alan is our resident engineer. Thank you for that, Alan, who's helped us put this deck together. Alan, could you also tell our audience, if they have a project they want help with, how do they communicate with us?
One of the easiest ways is to contact any one of us from the contact page. So definitely take a print screen, or you can email dlandy@pepipe.org. But we'd love to talk about polyethylene. We'd love to talk about your projects and help you in any way, shape, or form that we can with all of the resources that all these wonderful speakers have accumulated in great experience over the years. So definitely, please don't hesitate to reach out to us, and I'll figure out how to share the poll. Thanks.
Thank you. And Jim Johnston, if you could come on and tell us, we're talking about all these cold weathers and fusing pipe in cold temperatures. Talk to us a little bit about the polyethylene itself.
So I think the piece that we see most of the time is that the service capability of this material is so great. Service temperatures themselves, minus 40 degrees to 140 degrees. And the piece that really comes into play there is that glass transition temperature, where it's going to get brittle and fracture, is minus 130. And I'm hoping that most of you who clicked on the poll there that said your regular temperatures below below zero don't see minus 130 degrees. So this material definitely stays very flexible and capable throughout that entire piece. And on the other side of that, you've got the expansion and contraction, and the easy way to remember that is the 1-10-100 rule. It expands at 1 inch per 10 degrees Fahrenheit per 100 feet. It's also very restrained. So it takes a very small force to hold that in place. So once it's buried, you're not going to see that expansion rate. But on the surface, you will see those pieces come into play. If you compare that to carbon steel, it's a huge force. Even though that expansion volume is not as large, the force there in a steel pipe versus HDPE, in this example, 8,000 pounds versus 321 pounds. So your restraint capability, restraint blocks are much easier to maintain and install and calculate your needs throughout that entire process.
Yeah, Jim, PPI's done a lot of study on that too, and it's pretty interesting about how just backfill restrains polyethylene just with the weight of the backfill. And this
Absolutely.
illustration is fantastic. It just really doesn't take much to restrain poly and keep it from moving. And I would like to say that this thermal expansion and contraction formula is an unrestrained polyethylene. So if that soil is holding on to it, it's not really going to move very much. So I'd like to say it's a temporary condition during construction, unless you're running an above ground polyethylene installation.
Laying on the surface of the ground unconstrained. Absolutely. Yeah.
Right. What do you have here, Jim?
So fabricated fittings, bending radius, the material itself has a minimum bending radius. You think about a straw, anything that you bend, you're going to be able to bend that until the point that it kinks. But the minimum bending radius is a little bit different during cold weather. So the minimum bending radius if we look at that DR7 through 9, is 20 times the pipe OD. Now, obviously, that is, if we were comparing that to any other rigid material, you're not going to get really very much bending radius at all. But you do have to take that into account. You want to take that into account. It's also why cul-de-sacs, other things, it's the ideal project for polyethylene, because it can be coiled around that cul-de-sac. You don't have multiple joints laying in. You don't have multiple miters. You don't have multiple components. But as we're talking about cold weather, you do need to take into account what your bending radius is versus the middle of the summer if you're doing an installation, especially in this above ground type situation. You still have that great flexibility, but it is going to be a little bit different in the cold weather, and take that into account.
As we move into this, Jim, we're starting to back up in chat. So we're going to refer you, if you ask a question in chat, we're going to refer you to Q&A so we can keep track of it. If you don't want your name published, just say, ask for a one-on-one return. And we do ask that our responders sign it so you know who you're talking to. So please do not ask questions in chat. Jim, take it away.
Okay. So what is polyethylene itself? It is a semi-crystalline polymer, meaning that it is a mass of different materials, thermoplastics. It can be continually reheated and softened and hardened by cooling. It's reversible and repeatable, so you can do it over and over and over again. I think of it as that giant bowl of spaghetti. It gives you that system that's out there that all those pieces interconnect with each other, and when you melt it, it all comes back into the original form. So that method of heat fusion is really turning it into a molten material and then returning it to its original form, and gives you that continued strength and no change in overall density or area control. So when we're doing heat fusion itself, you've got two surfaces. They're heated they're heated over time in the pressure. Golly, I'm having a hard time. Across those surfaces, when they're brought back together, the crystals will then reform across each other and over time re-engage over time. When cooled, those molecules return to that original semi-crystalline state. And back to, if you were on at the beginning of the process when Peter was showing some of the samples, when you look at a cross section of a joint, you see very little, if any, differentiation in that joint itself. It is returned to its original form in that process, very much like the original extruded pipe.
And Jim, when you look at this and you compare it to PVC, which is, now to the dominant, metallics are no longer dominant. Now it's plastic. It's either PVC or polyethylene. PVC and polyethylene are very different materials. You don't see PVC to be able to do what polyethylene does. Is that right?
That's right. It is a much different material. There is fusible PVC out there, but in general, what we talk about is that form is not a thermoplastic. This material is, again, going to bond to itself. There's no chemical bonding that's occurring. In this video, you're seeing the two ends of the plastic that were heated and brought together, and then that molten material is squeezed together. Some of that extrudes to the OD of the pipe, some to the ID of the pipe. But you have that intermingling of those molecules at that interfacial joint, and that's
Jim,
Go ahead.
Whenever I do my events, across the country, we always start with butt fusion, because people that don't have much experience with it, they're like, I don't really get it. What is this fusion thing?
Right.
And then they're like, oh my gosh, you get them directly opposite one another. You clean it, you shave it, you heat it, you fuse it, and all of a sudden, you end up with these steps that create this pipe, whether it's a 4-inch pipe, which we just saw, or whether it's a 48-inch pipe, DR11. We've got DR11 going in today. It's just really extraordinary. Tell us a little bit about this facing operation.
So the facing operation brings the two ends. They're held in parallel with each other, and then they're faced off. So it's basically a knife edge that is facing the two ends of that pipe and exposing virgin material. So this takes any oxidation, any misalignment of the two ends, whether it's the cut piece there. So they're making those square and parallel with each other and exposing virgin material. So you clean that material, you shave off the ends of it. The next step is to heat it. It's brought together against a heating plate. And those two ends are melted. The machine is opened up. The heater plate is removed, brought together under a specified force Peter talked about ASTM F2620. It goes through all of the characteristics there. And you hold it until that joint has cooled down sufficiently to the point that it is ready to go. And that's
So
what it
that's
is. It's very simple
the reason,
at the end of the day.
and the reason we're spending time on the process, because it's all about the process. And no matter what the weather is, we want you to follow this process. And this process is true even with butt fusion or electrofusion. So 90% of those fusions are butt, 10% are electrofusion. And with electrofusion, we don't follow ASTM 2620. We follow either the manufacturer's procedure or the Municipal Advisory Board of the Plastic Pipes Institute procedure for electrofusion. And they have two. They have one below 14 inches in diameter and one above 14 inches in diameter. And you can go to their website and get a copy of that, or we include that in our engineer's package. In Europe, electrofusion is even more popular than butt fusion, yet in North America, we use more butt fusion than we do electrofusion. One of the key elements of electrofusion is that there's two clean processes, and you've got to make sure you follow those steps so you clean it that second time. Chris Waite may come on and tell us a story or two about electrofusion. And here on this right side image, we see those couplers. So in butt fusion, we have a heater plate introducing heat to the ends of the pipe. We call that the heat soak. But in electrofusion, we have copper wires that are introducing heat to the ID of that coupler and to the OD of the pipe simultaneously. And then you can see on the left-hand side there, we've got a cold zone and a hot zone or a fusion zone. In those cold zones, once that fusion zone melts all that resin, those cold zones dam it up and hold it in place. It's a fantastic procedure, and it's all made possible by that electrofusion processor, which needs to have power. So we need to have power on the job site. So that generator's got to run both a butt fusion machine, if it's a small diameter one, or it's got to run that electrofusion processor. Many of those McElroy pieces of equipment are self-powered, so they don't need a generator. But on the electrofusion side, we've got to run a generator. And Chris, if you could come on, what kind of generator are we looking for to run those electrofusion processors?
So Peter, all the generators out there, or all the electrofusion manufacturer processors out there will give you a specification based off of their machine. The biggest thing is to make sure you have the right wattage and look at your elevations. If you're at a higher elevation and that machine tells you need a 6,000 watt generator, you need to look at the duration for that generator based off of the elevation that you're actually at. I mean, I've done electrofusions from 11,300 feet elevation where we had to double up generators all the way down to sea level where we could run the standard generator that the manufacturer recommends.
You're on mute, Pete.
Excuse me. Thank you, Alan. Alan, before we get into safety, could you tell us if there are any questions you want to share with the full group?
We've been having great questions that are rolling through. So our bench is so excited about answering them that they are being extremely thorough and sometimes providing multiple opinions on the same exact topic. So they're just being even more so thorough. But thank you very much, everybody. We did have a really good question about the spacing of the concrete anchors in that river body or water body that we showed you. Each one of those spacing designs are going to be very site specific. So if you have a water body crossing that's sitting on the bottom of that water body to use HDPE and concrete anchors, don't hesitate to send out to dlandy@pepipe.org or myself at aambler@pepipe.org. All of those are specialty engineered scenarios as that goes there. So what we're looking at now, until Pete or Jim wants to come back on, is that safety is that #1 priority. So migrating from design to construction, not as many design engineers have safety meetings, even though it's very important to be able to do so. But in construction projects, that is a daily occurrence to make sure that we don't lose fingers or toes or anything else. So with all projects, regional things have specific needs as well too. So they are going to tell you guys, everybody out there, what to do in cold weather, and that's why you're here to begin with. So I'm so happy that everybody joined us.
All right, thank you, Alan. All right, so one of the things about the pipe is you don't want to drop it. You never want to drop pipe or any other pipe. If you drop PVC, it's going to crack on you. Polyethylene, it may not crack on you, but the colder it gets, the greater the risk of damage. So we're talking 0 degrees, 10 degrees Fahrenheit. We want you to treat it with care. There's a story that Richard Colossa likes to tell of a pipe string that was going in Calgary, and it was a 36-inch diameter, and there was an accident at midnight. A drunk driver hit the polyethylene, and it cracked the polyethylene. Brittle, or more brittle than it would be at ambient temperature. PVC, on the other hand, is brittle at temperature, at 72 degrees Fahrenheit. Polyethylene is not. It doesn't get brittle until well below 0. But it does have reduced impact resistance in cold weather. So please be aware of that. If you hit polyethylene on warm weather with a sledgehammer, that sledgehammer is going to bounce back and hit you in the head. So in colder weather, you could indeed crack it like that car did at midnight. Coiled pipe is kind of interesting. So here we have a DR7 pipe that is being unrolled in the reel, and this is sub-zero temperature. And notice how it retains its shape. And it does it even more so in colder weather. So that is something to pay attention to. That uncoiling is a specialty. It's an advanced, you want your experienced people to deal with that. The pipe manufacturers, when they produce it on reels, they band it properly. So as it comes off, you may have to clip some bands. I've never personally uncoiled a polyethylene on a reel, but I do know that it is one of the more dangerous things you can do with polyethylene. So please be careful. Carl, could you come on and tell us a little bit about frozen polyethylene and how your products try to avoid that whole issue?
I can, but it'd be ruining the surprise, Peter. I'm going to go into that in my slides, but certainly there are two different topics really here. So obviously, what we try to do with pre-insulated pipings is to avoid freezing. That's the whole idea. In the event of freezing, there are ways to thaw out pipe, and it's generally with use of electric heat tracing of a specific type of design. That's a whole other seminar.
Yeah, we do ask that you don't use open flames, right?
Sure.
That you use heater blankets, that kind of thing does work.
Correct.
All right, Carl, let's see here. Now we've got Jim Johnson. Could you come on and talk to us about temperatures and polyethylene at various temperatures?
Yeah, so basically you want to be doing, you want any system, anytime you're doing it, whatever weather you're doing, you want to have your pieces in similar temperatures, whether that's electrofusion. In this particular case, you want to make sure that your electrofusion fitting is at roughly the same temperature as your pipe. And so if you're in a protected zone, or if your pipe, or if you're keeping your electrofusion fitting, for example, in the truck, but you're fusing on pipe at 15 degrees Fahrenheit, you really want to bring that fitting out and acclimate it so that you don't have a differential there. You do have that expansion component that goes into play, or a fitting of any kind. So you want to make sure that those two are in similar temperatures so that they are moving in the same format, and that way you've got good connections and good continued joint process and size. Everything else, it makes it much easier if you have a fitting that doesn't go on your pipe. It may be just the difference there. From the hydraulic equipment standpoint, you need to be aware of your your requirements for your hydraulic oil. So if you are in a northern Alaska, northern Canada, subarctic circle zone, you want to be considering whether it's your truck or your cat or your generator or your fusion equipment, all those components, you want to be using the appropriate diesel, the appropriate hydraulic fluids, and look at those viscosities and make sure that your equipment is going to be running in the way that you expect it to, because you have so much variation, or can have that. And all the manufacturers out there, whether it's McElroy, our equipment, this is an example from one of our equipment guidelines, or your generator or any of your components, are going to tell you what hydraulic fluid to use for the range to maintain that viscosity throughout. And as we talked before, we're really not changing the procedure, but we want to make sure that we're adapting and making sure the equipment runs correctly. Make sure that your generator that your generator is going to output the amperage and voltage that you need in the given weather conditions. Let's say you're also at altitude. Make sure that you're taking and considering what your output is at altitude. So varying power can affect the performance of an electric fusion machine or an electrofusion machine. And so you want to make sure that you are aware of the conditions and know what you're doing. If you're used to that cold weather, then you're also doing that in a general term. You want to use tools to align that pipe. We talked about all the components. This is true again for any fusion, but it's especially true with cold weather, inclement weather. It gets it off the ground. It helps you direct that pipe. That pipe is going to be stiffer, so you're going to need better tools to help maintain that alignment, adjust for curvature, what other components, whatever other situations you may have out there. Use the tools that are available to you to reround the pipe, to align the pipe, to elevate that pipe, keep it clean, keep us going, keep it going on at that level. In this, so pre-insulated and heat trace pipe, you're going to flip over here, Phil, or Peter.
Yeah, time for Carl.
Okay.
Okay, thanks, fellas. Yeah, I'm going to talk about well, pre-insulated pipe and heat tracing specifically in cold climates, and really what it's all about is preventing freezing. Next slide. Do I have control of the slides, Peter, or is that you or Alan?
Pete's got it, Carl. So
Oh,
I
okay.
think he's trying to
Okay.
work out an intermittent issue that we seem to be having. So
No.
just ask to advance, and he should be able to do it.
Okay, sounds good. I'm going to talk a little bit about the materials we use on HDP pipe. But before I get into that, I think it's important to say, and it's no coincidence, that most of the piping that we at Eurocon factory insulate happens to be HDPE. It's for obvious reasons that this is the most cold friendly piping material, and it's by far the majority of what we insulate, especially for northern climates. We use polyurethane foam that we apply to the HDPE pipe in a number of different methods. The one that we're showing here is what we call our contour or continuous rotating system. In this example, we spray the foam directly onto the pipe, and then we apply an extruded jacket directly over. You can move to the next slide, Peter. So this is a photo of a polyethylene jacket, which is applied directly onto the polyurethane foam, which sets up super quickly, and it can support its own weight through this continuous rotating system. Next slide. And that's just a picture of the piping coming off the main equipment. And next slide. And here's a good sort of side view of a finished polyethylene pipe with that would be a standard. Generally, it's a standard 2 inches of polyurethane foam with an extruded polyethylene jacket. So basically what the polyurethane does is buy time. That's what freeze prevention is all about. So this is a good sort of table to illustrate what you get with 2 inches of polyurethane foam in the event of a no flow in the pipe at a continuous cold temperature. So if we take a 6-inch pipe as an example, at zero degrees Fahrenheit, if there was no insulation on the pipe and there was a no flow condition, you got about 18 hours before you have a solid ice cube in that pipe. And with 2 inches of polyurethane foam, that bumps it up to 300 hours. And if you can slide over to the next part, it's basically at a colder temp. Oh, back to the same one. Sorry, Peter. Basically at a colder temperature, the change is less dramatic, but still pretty impressive. 9 hours in a no flow with a bare pipe to freeze solid, and 155 hours at -30 with 2 inches of foam. Next slide. To complement the polyurethane foam, really the urethane foam is doing the heavy lifting. However, in certain cases where it might be a critical line or no flow conditions are expected, we complement with electric heat tracing. And basically the electric heat tracing only kicks in when absolutely necessary. For the best types of solutions when it comes to freeze prevention, we use what's called a constant watt thermal cable or a constant watt heat trace cable. There are different types. Essentially what that means is there are sensors that are placed directly onto the pipe under the insulation. And when a cold temperature is detected at the bare pipe under the insulation, then and only then will a controller kick in, and on comes the cable. So it's not like the cable is running all the time. Many of the sort of further the installations in the far north are diesel generated power. So electricity is rather expensive. So we're pretty careful on how we insulate and heat trace these pipes. In the extreme event of very, very long heat trace lines, we can go about 12,000 feet from one power point. And this is just a photo showing a thermostatic controller and its connection at the bare pipe. And then on the left, you'll see that's a sort of a standard heat trace cable that runs through a conduit that runs along the bare polyethylene pipe. So some of the most common applications that we see for pre-insulated piping in the freeze prevention genre, it would be the biggest one is shallow bury. So this is where, for many reasons, it's difficult to get underneath the active frost zone. So it might be because it's rock, it might be because it's sand, but for whatever reason, it's difficult to get down below the frost zone. So essentially, we pre-insulate the pipe, and it's installed directly in the frost zone. And we generally say, you don't have to be on some huge crusade to get down to the bottom of the frost zone. Even if you're a couple of feet down, 2-3 feet down, that's sufficient. The insulation does its work, and the heat tracing complements the insulation if required. Another very common use of pre-insulated pipe is in a municipal setting for bridge crossings. We see this all through the northern US and into Canada, where it might be difficult to do a drill underneath a river, so you have to cross it, and therefore you're exposed to the ambient temperatures. We insulate and sometimes heat trace these lines, and you'll notice that the jacketing in this case is a metal jacketing. So often for these types of applications, we prefer a bit more beam strength. So we elect to go with either could be a stainless jacket, sometimes it's aluminum. And in the example on the left, that's a big 30-inch pipe with 2 inches of foam and a galvanized steel, what we call spy wrap jacket. Pretty common.
So Carl, on the image in the upper right, do you manufacture the harnesses that's holding the pipe as
We do
well, or
not.
do you?
No, we
So-
don't. That's typically supplied by local distribution. It's pretty common. The trick here, of course, is that the pre-insulated piping with urethane foam, because the urethane foam has very strong compressive properties, we can support the entire system from the outer jacket. So in other words, there's no pipe shoes directly on the poly pipe itself. Everything's supported from the outside jacket. So you don't have that thermal bleeding that you would if you were field applying insulation. But those hangers are pretty common, Peter. This is a good picture of a quite a large diameter HDPE pipe bridge crossing in, I think this is in the province of Quebec. So you can see that this is just prior to buttoning up the joint. So typically the piping would be either fused on the side of the bridge and then pushed through on rollers, or in some cases, depending on the joining, as Peter said, if it's 10, sometimes we see about 10% electrofusion couplers. We can use electrofusion on these installations as well. It just depends on the application. Sort of moving over to more to the industrial side of things, pre-insulated HDPE pipe is pretty common in the mining sector. What we often see here is piping that's directly laid on grade and just runs from A to B, and these runs can be fairly long. And we see these in hard metal mines in northern climates, all the way up to the Arctic Circle, where again electricity tends to be rather expensive. So we're careful when we're heat tracing, but the heat tracing comes into play and it's pretty critical.
All right, Carl, Alan and I are going to try to figure out and transfer it to him because I have a latency issue.
Okay,
All right, Alan, you got it.
got it, Alan. Okay.
Yeah, can you see my screen now? Still,
Yep.
Carl? All
Yep.
right, perfect.
Yep.
We're transferred, Pete.
Okay, I'll continue. In the mining sector, there are numerous sort of individual applications, let's say within the mining world. Another one is construction camps and fire lines. Pretty common for mine sites. The fire lines are interesting because typically these are required for insurance reasons, and the piping is polyethylene and it's pressurized water that's stagnant. So there's no flow in that pipe typically, and it would surround a small camp like you see on the picture on the left. And so what we do in that case is we of course insulate and heat trace, and we have the set point of the heat trace set a little higher than normal. So typically we run it between 10 and 15 C to give us a little extra conservative wiggle room. Next slide, please, Alan. More on the mining side, pretty common to insulate and heat trace polyethylene intake lines. We often will the photos on the left are a pretty good illustration of that, and then of course outfalls as well. Intakes are interesting. Typically we'll have a pump house directly adjacent to the water, and we don't need to take the insulation too deep into the water. Typically it's just through the what we would call the ice cap, and then we heat trace down through the ice cap, and the conduit in that case would be a closed, often a small polyethylene 1 inch, like CTS 1 inch pipe that we use as the conduit, so there's no water that can get in. Next slide, Al. Process pipe, same thing. Mining sector, often the pipe is laid either directly on grade or on sleepers, like the picture on the left. And we can go fairly long distances and maintain flow using the same techniques as just described. And in some cases, we may not have the luxury of having the time to have piping delivered to a plant to be factory insulated. Some cases, maybe the pipe's already installed, or perhaps it's a quick or a temporary application. And for this reason, we have a product called Pure Split Tube, and it basically it's 20-foot lengths of polyurethane foam that's split down the side, and this can be flipped onto polyethylene pipe in the field very, very quickly, and it's just as effective as the factory insulated version. The downside is there's no bond with the factory insulated pipe. There's actually a bond between the polyethylene pipe, the foam, and the foam and the jacket. So it's one moving piece together, like mechanically connected, like a sandwich. So in this case, it's a little different, but equally as effective in terms of freeze prevention. So we get all sorts of questions all the time, but here are a few questions that come up pretty often. And the big one is, will this pre-insulated pipe, this fancy urethane stuff, will it keep my pipes from freezing? Well, the answer is yes, to a certain point. In a no-flow condition, of course, over time, you're gonna eventually have a freezing pipe. So what we do in that case is like I mentioned earlier, we complement with electric heat tracing. So with the combination of urethane foam and heat tracing, that will get you a system or a solution that will prevent freezing. And it's pretty simple and extremely reliable. What do we do with the joints and the fittings? So basically at the joints, typically what we see with polyethylene pipe is butt fusion. And essentially we cut back the insulation 9 inches in general from the end of the pipe. This allows the guys in the field to get to the core pipe. Usually with a McElroy machine, we may remove one of the arms. The 2 faces of the polyethylene pipe are joined just like they normally would be. Nothing's different. The polyurethane foam is kind of going for the ride in effect. And once the joining is finished and tested if required, we provide usually it's a two-piece insulation kit, so half shells that would be applied in the field, and it can be either a heat shrink type sleeve if it's buried, or it could be a piece of metal or a slip of polyethylene that's slid over the top. So pretty simple and very easy to install in the field, even in very remote locations. Fittings are similar. We fabricate a fitting kit, generally in 2 pieces, that can be installed over whatever fitting is required, be it a long sweep, polyethylene standard fitting, something custom, an assembly, a valve, a clean out, you name it. We can build a kit that will fit that fitting and be installed in the field. Standard lengths for pre-insulated HDP are the same as standard HDP that's bare. So typically 40 footers or 50s. We can go longer. We're really just limited by the length of the truck. But typically on mine jobs, which are long runs, we're 50 or 55 footers. And another common question on the municipal side, does a pre-insulated pipe meet H20 loading? And the answer is yes. The compressives are pretty impressive. They're somewhere between 2 and 300 PSI system compressives. So plenty strong enough to meet H20 loading, even at a foot or 2 below the surface. Minimum bend radius. This one comes up all the time. Essentially, with polyethylene pipe and a polyethylene jacket, so not a metal jacket, but a poly jacket, which is the most resilient and preferred jacket, we apply the same calculation that you would with bare pipe. So as an example, I think, guys, it's DR11 is 25 times OD, right? Minimum bend. So it's the same with the pre-insulated polyethylene pipe. We just take that 25 times OD of the outer jacket now, not the core pipe itself. So it remains very, very flexible, even with the polyurethane foam. That's the beauty of polyurethane.
Your memory's spot on, Carl. Absolutely. 25 times that OD. So just a reminder, everybody that wants PDHs at the end, you can supply the survey to us. We've done really well keeping everybody to this point. Thank you so very much for your constant attention. Just a reminder, we've got about 20 minutes left to get to that 75-minute webinar. So I believe we've fixed Pete's latency issue behind it. So definitely our apologies for technical problems through this webinar, and we really do appreciate your patience. Take it away, boys.
Two quick questions left here. How do I decide if my insulated pipe requires heat tracing? Well, essentially, this is a question of doing a heat loss calculation, or what we call a time to freeze study, and which we can do, and effectively we can predetermine how long you've got before freezing sets in, and then in increments as freezing goes from the sort of outside of the sort of the outer part of inside the pipe towards the middle. And it will basically gives you an idea of what the worst case scenario would be in a no flow condition. And based on that number of hours, one can decide whether heat tracing might be a good idea. So, if it's a week before freezing and it's a municipal line, likely there's going to be, resumption of flow before you have a big problem. But if it's a mine process line that is super critical and that could hold up a manufacturing business, then heat tracing is probably worth putting in. It's pretty inexpensive and extremely reliable in the sort of just in case scenario to make sure things are redundantly in good shape. And smallest and largest diameters for polyethylene that can be factory insulated. Basically, we go from 1/2 inch or 1 inch pipe all the way up to 48 inches.
Well, great job. Really appreciated that. Your section isn't something we've included before, Carl. So I think you did a great job. And your email will show up in the contacts. So thank you very much. Chris Wade, if you could come on. There was a question that just came on about, hey, when should we start preheating? And according to page 13 of 2620-20, Chris, it says, when making butt fusion joints at ambient temperatures below 3F or 16 Celsius, go ahead and preheat. They say to preheat, Chris, but they don't say why. Help us understand that.
So the biggest reason for preheating ultimately is you have to get the heat to permeate out through the wall of the pipe. If you don't preheat the pipe and you get down in the colder temperatures, what you run into is the fact that you could still very potentially get a cold fusion out of it. It may look good, but ultimately the thing you're wanting to look at is in between the beads. If you start seeing a white line there, it's stretching the polyethylene material. So it's not actually mixing the molecules of the polyethylene at that point. So that's something to look at when you're doing that. If you're seeing that white line, you need to stop and either preheat more, start your fusion process over, obviously, but preheat more to get that pipe up. It's really nice if you can get it up to 40 degrees F, or even maybe up to 50 degrees F, and that can be done a various amount of ways with a heat blanket or a non-flame heater or something like that with a tarp over the end of the pipe. So as you're pulling those into your fusion machine, they're already preheated.
Well, back to
Peter,
PPI's
if I could
guidance.
add, if I could add just one real quick to that is, you're also bringing a very cold product against that heater. And so that helps you eliminate that heat shock that happens there. So you're maintaining the temperature of your heater much better. So you're bringing that up so that it's not as think of putting an ice cube on a frying pan. You're not going to have any sizzling issues like that. That's a bad example in that terms, but you're not shocking the heater.
Well, thank you for that, Jim. Chris, I was really excited to learn that. I always thought preheating was an option. I didn't realize it was a requirement until I reread that standard. But really, we ought to go back to PPI's guidance and put it in a tent, Chris, don't you think? Or use some sort of structure so we don't have to fuse at such a low temperature?
Not only is it going to make your operator more comfortable by having it in a structure, but it's going to make your fusions more reliable. Just as Jim brought up about the heat shock of what's going on and the stretching of the polyethylene material, it takes your open close times down. I mean, the object is to open it, inspect and get it closed as fast as possible. But at the same time, if you've got wind and you're out in the wide open, it's going to shorten those times tremendously to where you could get cold fusions. And we all know that cold fusions are actually going to hinder you in the end, because you're going to have to go back and fix all those later.
Yeah,
So,
good stuff.
Pete, before we go too far, being a boy from Florida, I'm not that familiar with cold regions in this area, and I love the conversation because it indicates nuance. It really indicates that people with experience about having these issues are able to share that information, which is not always written in the lines of all the manuals all the time here. So we got another question before I lead into something that I never thought about either. Is there a visual cue that shows that the pipe ends are preheated enough? That's one for Chris and Jim. And then we got a really cool one for Carl, if he's ready to come on camera once you guys finish this. Can you actually use horizontal directional drill for a pre-insulated pipe jacket in that manner? So Chris and Jim and Pete, if you want to take away on the visual cue, that would be perfect right now.
Yeah, I
All
can.
right, Chris.
Yeah, go ahead. Go ahead, Chris. I can take care of the other question.
I wouldn't say so much that there's a visual cue as much as having your infrared pyrometer there to make sure that your pipe temperature is up. You can have snow and ice on the end of the pipe. I mean, obviously we're cleaning that off. You want to make sure there's no moisture, but the biggest thing is just taking your infrared pyrometer and making sure that that pipe temperature is up. And don't just test it on the top where the heat's blowing on it. You need to test all the way around it just to make sure that it's not just one hot spot on the top of it. The same thing goes in the summertime. And we're talking about cold weather fusion here, but when you got your pipe sitting out on the ground in the summertime, and you're getting sun on the top side of that pipe, the bottom side of that pipe may be 20, 30, even 40 degrees cooler than the top side of that pipe. So you need to be paying attention to that aspect of it too.
Yeah, and
Cool.
I agree with all those statements. You're really, I think the guidance in A11 is 30 seconds to a minute. I think I don't have the exact piece in front of me right now. But basically you're wanting to just bring up that temperature of that into that pipe. Again, think about something that's just been sitting on the ground out in the cold. You're now in a shelter. You want to bring that up so that you're not sucking all of the heat out of the heater. And you also don't want to have it exposed for too long. Remember that you have faced off that pipe and it is as clean as it will ever be. So you want to give it enough time to give it some heat, but not expose it to the air so there's any contamination, if there's any blowing dirt or anything that's going on around there as well.
All right. Thank you, Jim. Carl, question that Alan asked.
Yeah, good question about directional drilling pre-insulated pipe. The answer is yes, this can be done. We do it fairly frequently. We take care in being sure that we supply basically a cone where the drill head would be attached to the pre-insulated pipe. So we're pulling on the core pipe and the jacket at the same time. And we pay attention also to the joints. So typically we'll have a double joint so that the friction, any friction that might develop through the pulling so that survives, the joint kit will survive that. Two types, we see direct drilling where you use bentonite or other lubricating fluids directly onto the pre-insulated pipe jacket. Or another way is to pull a sacrificial conduit, like a thin wall poly jacket, and slide that pre-insulated poly through that conduit. So numerous ways to do that, and it's pretty common.
Yeah, so you've developed techniques. That's very cool. Hey, Chris, come on and talk to us about what we've been seeing on the screen for the last 5 minutes. Got some George Fisher product in there and some marine environment. Oh my gosh.
Yes, sir. What you're seeing here is actually one of their repair couplings. In the picture, you're seeing two different situations. You're seeing a repair coupling that's actually a restrained coupling that George Fisher makes on the left-hand side in that left-hand picture. And then you're seeing a spool piece that you can put in too. Just two different repair methods that you can take to fix polyethylene if you were to have a line strike or you were to which most of your repairs are going to be line strikes because you don't have very many failures in polyethylene. But the spool piece and the repair coupling are the two most common repair and maintenance situations that we have out there. Here is the up close of that George Fisher repair coupling. You can see inside there, you got your rings that the bolts are going through, but that black ring that's between there has actually got some little teeth in it that makes it a fully restrained coupling. So you can put that in and your pipeline system is still fully restrained even when you bury it. And you can use these as a permanent repair on your system as opposed to just a temporary repair. And this is just a flange adapter here. Looks like they're going to drop in a spool piece or connect on to that flange adapter, and that's going to be the same thing. It will be a fully restrained joint still.
Thanks, Chris. Great job. I want to thank or acknowledge PPI and ASTM. I mean, that's where we get a lot of our guidance, but we have guys like Carl and Jim and Chris Waite to help us understand how things really happen in the field. And here on the next slide, we have the actual document, ASTM F2620-20. You will not get this in our engineering package. We cannot give it to you because it is copyrighted. You have to pay for it. It's relatively inexpensive. But the chapter is an appendix. A1 is cold weather procedures. We recommend that you purchase that document and make those 2 pages a regular part of your polyethylene design repertoire. And then, of course, we have the Municipal Advisory Board's document, which is free of charge. You can grab it on their website, or it's part of our engineering practices. So here is a slide to take a screenshot of. It's like the 10 major things that you need to do to make sure you can conduct a fusion and that your pipe is going to fuse the way that it's supposed to. I'm not going to go through each one here because we're going to try to make up a little bit of time because we've got some good slides here that you're going to want to see. But certainly, keeping moisture out of the fusion zone, plugging the ends, not just to plug the ends, but to keep the animals and the weather away from creating a vacuum inside or blowing the dirt into the fusion zone. Next slide, Alan. This is my favorite. It's cold, it's raining, be patient. That's all you have to do. You change the conditions, you do not change the procedure. That's why we spend so much time talking about the procedure, because we want you to fix the conditions. This is a very consistent image that we see in the winter is polyethylene pipe looks like this. But if you'd capped the ends, you would have kept the snow out of the inside. And we're not expecting you to put a tarp over it, but we are expecting you to spend that half hour to clean off the OD of that pipe. And I also think it's important. I mean, remember that story about the car hitting the pipe, that before that pipe stream goes in the ground, because polyethylene is a little bit more brittle when it gets colder, you've got to inspect it for damage. And remember that 10% rule. That image on the right I shot up in Michigan, that was only a 3% gouge in the pipe. That was a 3.5-inch pipe wall thickness. You have plenty of room there. All you got to do is cut that off and go on and look for the next one. And then, of course, we have that car and the car tire hitting the polyethylene. So yeah, examine the pipe and remember the golden rules. So that enclosure, everybody's got a bunch of different types of enclosures. You don't want excessive heat, but you do want to give that pipe time to get closer to warm all the way around, not just a half. If you only warmed up half of that pipe and you did a fusion, that bead would be so totally different. Chris, tell us, what would that bead look like if I did half of it proper? So from 9 a.m. to 3 p.m. was proper, but below that, from 3 p.m. to 9 on the bottom half was super cold when the fusion was done.
Ultimately, what you got going on there is you're going to have a nice adequate bead on the top, but you're not going to have an adequate bead on the bottom. And that's when, as an inspection side, you're looking at that bead, you got to compare each bead to itself all the way around the full circumference of that pipe, and they should be even to each other. So if you're getting a 3/8 bead on the top on large diameter pipe, but you're only getting an 1/8 inch on the bottom, you don't have a sufficient heat soak, and your pipe's not going to hold the way it should.
Thanks. I love this one because here we have, Jim, what do you call the McElroy pipe stands that are hydraulic that are shown in this image?
Called poly horses.
Yeah, so here's a polyhorse setup where one person can take off the pipe from the flatbed, put it on the polyhorse, and he or she can move the pipe into the fusion zone by themselves. And there's the quick camp, which is the gold standard for a proper contained fusion space. And once again, there's that image on the left where the guy cleaned up that pipe correctly before it came into the fusion zone. Next slide, please, Alan. And there's a closer up look of that quick camp and that hydraulic machinery that changes the elevation of that polyethylene pipe as it's going into the quick camp. This is one of my favorites that shows how to plug the ends of the pipe and why to plug the ends of the pipe. So in the gas industry, which is 99% polyethylene in distribution, they ship the pipe with capped ends on it. We're not doing that. We cap it when it gets to the job site. So maybe we're selling more pipe that way. I don't really know, but this is why you cap the ends on the job site. Next slide, Alan. And then ensuring that this is just basic. We're just reinforcing some of the things that we've mentioned to you earlier. Next slide. So here we have one of Mike Whitehouse's colleagues there at ISCO on the left. They've got two operators running 4 different fusion machines in a protected space. I mean, that's brilliant. Now, remember when you're doing fusions that you have to wait for the fuse cool cycle, so sometimes you've got some downtime, add another machine and you won't have much downtime. That image on the right, sorry, Alan, I'll go quick. That image on the right is exactly what not to do. You got to do a better job cleaning that snow. Next slide. And then here we have in the bottom row, we've got heater blankets. These things are commercially available. If you're working out in the winter months, you probably ought to own some of this equipment. Go ahead, Alan. And back to the preheating the pipe. Do not heat the pipe greater than 120 Fahrenheit. So there's a rule. Use multiple heaters. Do the top and the bottom. Do the left and the right. And you will end up with a better fuse and that will pass that inspector's critical eye. Here's one that Richard Kloss has sent to us. Richard's on the bench answering those questions. What a great way. You don't use a heater blanket. You only have one heater blanket. You just put that tube around the end of the pipe and blow some hot air on it. What a great way to accomplish the same task. One of the things that people don't really talk about is keeping that basket clean. And particularly when it's cold, I mean, that's the last thing you're going to pay attention to, but you can end up with some contaminants on that pipe. And this is true in cold weather, bad weather, good weather, doesn't matter. Keep that basket clean. Next. All right, summary, cold weather considerations. We're getting close. Don't drop the pipe. Makes a lot of sense. Provide adequate enclosures. Use tents. Protect that fusion zone. There are a lot of ways to do it. Protect the pipe, protect the fusion zone. Make it nicer for that operator to do his or her job. Use space heaters, warm air, heater blankets. Preheat the pipe when it is 3 degrees or colder, or use a tent. And if it's 3 degrees outside, but it's 40 degrees inside, you are good to go. And remember, PPI's guidance is they want to see you do fusions at 32 degrees or warmer, preferably 40F or warmer. That is the guidance. Next slide, please. All right. Also, the thermal effects that are on polyethylene are pronounced in colder weather for obvious reasons. Also, when it comes to electrofusion and you're trying to do a butt fusion of a coupler, Chris, come on briefly. We've got a couple of minutes left. Could you explain the proper procedures to butt fuse a cold 45 or 90 that's been fabricated? What are the things that we need to pay attention to?
Ultimately, the first rule of putting any fabricated fitting in the line is to make sure that the pipe and the fitting are acclimated to the same temperature. That's going to save you a lot of headache, but make sure you're not pulling on them fittings. If you're putting stubs of pipe on there to set it down and fuse further away from that fitting for a bigger bell hole or something to that effect, make sure that you're not lifting by the fitting and you're adequately supporting the entire piece that you're putting down in there where you're not pulling on those fusions at an angle, because that will or can have an effect on the fusion in the middle of a fabricated fitting.
So Chris, we have competing guidance here. So in the electrofusion world, the guidance is you're supposed to keep that coupler, the bit, let's say we're doing 12-inch, and that coupler is supposed to be in a bag in a structure, yet you're outside and it comes to you warm and your pipe is cold. So how are we supposed to reconcile that and keep that electrofusion coupler safe from the elements?
So ultimately, it's going to get to the preheating of the pipe side at that point. You want your coupler and your pipe to be really close to the same temperature. So whether you're putting heating blankets on the end of the pipe to get the pipe up to the temperature of the coupling or letting the coupling cool down, you can keep the coupling in the bag. It's not going to hurt anything. You want to limit the amount of exposure outside in the elements, but make sure that you're taking that coupler and getting everything acclimated to the same temperature. The same thing goes in the electrofusion world as with your processors. You need to make sure your processor's out where you're actually going to make the fuse, because they will adjust your heating time based off of temperature. And most of the manufacturers say 62 degrees. Anything above 62, it may start knocking a few seconds off. Anything below 62, it may start adding some seconds on to the time that it says on the label for the electrofusion.
Well, great job. I really appreciate the color, Chris. You're an awesome speaker. Thank you. And Carl, so are you. And Jim, what a wealth of knowledge. I want to thank our audience. We've only lost 5 people across the 75 minutes. So thank you for your attention. We are going to post this by next Monday to YouTube, so it will be available for your colleagues. Alan, could you come on and tell us how to grab our PDHs again, please?
Absolutely. So if you'd like a PDH for this, stay on, complete the first question of the survey, and then tell us what your license number is, what state you're in, and fill out that survey. Also, if you want a PDF of the PowerPoint presentation that we've done today, please send an email to kanderson@pepipe.org, or as you can see on the contacts list here, dlandy@pepipe.org as well. So we're happy to share those. And that YouTube channel that Peter mentioned is absolutely ripe with great information, including a new technical note series that we're unveiling in 2024 here. I happen to be Dan Landy and Peter's brainchild to be able to tell you a quick 2 to 5 minute summary of one technical topic. So that way it's nice and succinct, but thorough at the same time. Great job, Pete, and everybody else.
Yeah, so you'll see those technical notes in our pre-show deck. So what we did today was side bend testing. In 3 weeks, we're going to do Paul Brodsky from McElroy is going to talk about the training process. Thank you to our audience for participating, our speakers. Great job today. And thanks again to the bench for killing it and keeping those 45 questions going during the talk. We'll see you next time. Until then, we'll see you on the road.